In this video, we continue from the last time where we computed, or rather we wanted to compute this integral 1 over square root of u squared minus 1. We proceed to give this integral a name and call this I1. I1 is equal to this integral. What happened in the last video was we used a substitution. V is equal to square root u squared minus 1, and then we wanted to see what this substitution does to the integral, and this is roughly what happened. What happened was, and let's call this new integral in terms of v as I2. What happened was this became another integral which was integral 1 over square root v squared plus 1 dv. And the point was, well, I wanted to do some integration, integral 1 over square root u squared minus 1, and instead we landed up in something which had the same thing, the minus 1 getting replaced by a plus 1. Okay, whether it's u or v does not make much of a difference. It's actually the minus 1 became a plus 1. And that sort of was a bad point. The only good point that came out of that was, if I know how to integrate this, then I also know how to find out I2. So I2 and I1 are connected. If I know one of them, I know the other. Okay? In this video, we are going to take a slightly different stance. We are going to explore the neighborhood of I1. And for that, let me write out I1 once again. And I propose this potential thought experiment. What happens if this minus 1 were not even there? If this minus 1 were not there, then this is how the integral looks like. And of course, I want to give this a different name. Let's call this I3. I3, everyone will recognize, is nothing but integral 1 over u du, and which is also well known to be ln of u plus the arbitrary constant c, where what I am calling ln is essentially the natural logarithm log to the base e. Okay, so this is what I3 is. Now we have a question. I1 and I3 are very similar, just that minus 1 in I1 is not there in I3. So can the answers be that different? And that's our hope. Maybe the answers are really not that different. Okay. So what we ideally want, is to show that I1 is equal to ln the natural log of something plus the constant, plus the arbitrary constant c. Of course, the main question is, what is this something? Okay, so what we want to do is, we want to figure out how to do a substitution so that we get, so that the answer sort of pops out. And note that what we essentially want is to express I1 as integral d of some v over v. And the question is, what is v? Okay, so if we can express I1 as integral dv by v for some v, then we know that I1 is equal to that ln of v plus c, and that v becomes that something. So what is this v? So this substitution, what is that? Okay, so let's proceed now. So we'll make a few attempts at what v can be. This in the earlier video, this from the last video, is one such attempt, one such failed attempt. Okay, so let's make a similar attempt here. Let me just, I don't want to write this once again. So let me copy and paste this. V is equal to this. And suppose my attempt is this plus 1. Okay, what can happen here? First of all, can we guess if something new will happen? If all of a sudden my problems will be resolved? The problems that we are talking about is that once we made that substitution, this v is equal to square root u squared minus 1, I2 was in terms of v alright, but it still had the pesky square root and the plus 1. Okay. Do we expect that problem to go away here? Well, not really, because 1 is a constant. So dv still remains the same. dv is nothing but u by square root u squared minus 1 du. And this, we remember, was the source of the problems about source of the problems in I2. So therefore, just by placing this plus 1, placing a plus 1, a plus a constant, this is not going to help us. And we also see that well, the dv has a u by square root u squared minus 1. So the next natural attempt is, so let me call this the first attempt. It actually is the second attempt after this one. Okay. So second attempt. Like I said, this one I should be calling the first attempt. This one is the second. Okay, let me just call this the second. And this one the third. Third time lucky, maybe. So let's try. V is equal to square root u squared minus 1 plus, well, not 1. Somebody may ask, what about some other constant? 5. Well, no help. Because if v is equal to square root u squared minus 1 plus 5, dv will turn out to be the same thing. And again, this term would become, instead of square root v squared plus 1, it would become something like square root v squared plus 5. Okay, that's all that will happen. Not much help. So we really need to change the extra function of u that we are adding on. 1, 5, these are constant functions of u, and they are not helping. And here I see a pesky u. So maybe the next step that we want to try is, okay, put that pesky u. What are we doing here? We are thinking about what to add on to square root u squared minus 1. And these failed attempts are trying to add on constants, which are not going to help. So what is the simplest non-constant function of u that we can add on? It is nothing but u itself. So therefore, let's attempt this one. And let's see what happens to dv now. dv is equal to, of course, that u by square root u squared minus 1. That, of course, stays. And now I have a plus 1 for this second u. For this isolated u, dv has this. And of course, I should place this in brackets. And I should be doing this in a better way. Okay, so this is what it stands for. dv is equal to u by square root u squared minus 1 plus 1 du. And as you see, this is nothing but u plus, let me write u plus square root u squared minus 1 by square root u squared minus 1 in the denominator du. Has that helped much? It has. If you notice, what has happened is v, which was equal to square root u squared minus 1 plus u, is now appearing in the numerator. So this I will write now as v by square root u squared minus 1 du. Are we sort of close to what we wanted? Are we sort of close to saying that du by square root u squared minus 1 is something like dv by v? Are we? Let's see. So if we take this equality, dv is equal to v by square root u squared minus 1 du, we can rearrange that to say dv by v is nothing but du by square root u squared minus 1. And this is exactly what we wanted. So therefore, if this were the substitution, v is equal to square root u squared minus 1 plus u, then the integrand I1, thus I1 is equal to integral dv by v, and we are home free, is equal to ln of v plus c, and write out what v is now. So therefore this is equal to ln of, let me put that in brackets, ln of u squared minus 1 plus u plus the arbitrary constant c. And that's our solution. That's the solution. So let's recap as to what happened. What happened was we made a couple of attempts. We failed in them. The rough direction was clear. The rough direction was given to us by the integral I3. So I3 was sort of similar to I1, but not exactly what it is. And I3 was expressible in terms of natural log. So that gave us the right direction that what we want for I1 is integral dv by v. And of course the question is, what is v? So we made a couple of failed attempts, and from there still is some sort of mystery or magic or something that we are uneasy with. That okay, in the third attempt we made square root u squared minus 1 plus u. What about if we had put it as some square root u or something? We could have gone wrong. So yeah, so there's some bit of magic here. And as a result, what we got was that dv by v for that specific v is equal to the integral that we want. And that gave us the answer. In the next video, we will try to derive this integral I1 in a much more principled manner. But that will sort of use some other tool, complex numbers. Thank you everyone. Bye.